Hello and welcome to the operation of electrical installation high voltage safety procedures. This training course is on the operation and safety of electrical installations above 1 kV. This course has been developed in-house by O'Hara Engineering to fulfill our requirements and the requirements of our clients alike. The objective for candidates is to learn how to operate, maintain and commission their installation above 1000 volts. The course will teach the basis of electrical plant operation, including the creation and implementation of documentation, the isolation of the plant above 1 kV so that works can be carried out, such as maintenance and replacement. It will teach how to carry out these works in a safe and efficient manner in accordance with ISEN 50110. The modules covered on the full training course include arc flash, operation of electrical systems in accordance with ISEN 50110, testing safety, high voltage safety rules and procedures, and the maintenance of high voltage systems. Protection systems will be covered here. This module will cover fault levels, protection discrimination, overcurrent and short circuit protection, earth fault protection, differential protection, current and voltage transformers and their application within the protection systems, transformer protection for both oil filled and cast resin type, transformer voltage regulation using online tap changers and offline tap changers, transformer voltage regulation relays. Fault levels. The energy released under short circuit fault conditions is governed by the capacity of the source supply. The capacity of an electrical system and its supply source depends on its size in terms of the generators feeding it. A small portable generating set provides a limited capacity to cause damage under short circuit conditions. A large transmission system fed from several large generating systems provide the capacity to cause very considerable damage. The increased generating capacity of a modern supply system has led to an increase in the prospective current available at the customer's electrical installation under short circuit conditions. It is not uncommon today for protective equipment in electrical installations to have a withstand the effects of energy released by fault currents of 30,000 amps or 30 kA or more. When a fault provides a path of negligible impedance and an electrical installation, a large electromagnetic forces are developed and great amounts of heat energy released due to the large currents flowing. The operation of an electrical welder demonstrates that even at low current of around 100 amps, they are capable of melting metal. It is not hard to visualize the damage of thousands of amperes could cause if uncontrolled. It is important consideration in designing and building electrical equipment and installations. Impedance. A transformer's impedance is usually expressed as a percentage of the primary voltage needed to circulate full load current in a short-circuited secondary. A 5% impedance is common. It means that only 5% of the normal primary voltage will produce full load current in the short-circuited secondary. It follows that the normal voltage, neglecting any impedance on the line side of the transformer, a three-phase short circuit on the secondary side would result in a current 20 times as great as the full load current flowing in the short-circuited secondary. To understand why circuit impedance plays such a critical role in limiting current at a fault, let's go back to the basic electrical theory. Ohm's law states that current is equal to voltage divided by the circuit resistance. At a constant voltage of 230 volts, substituting various resistance values in the circuit demonstrates how dramatically current levels increase as the impedance falls. This is a basic circuit wiring impedance. So, if resistance is 10 ohms, then the current is 23 ohms. If resistance is 1 ohm, it'll be 230 amps. If the resistance is 0.1 of an ohm, it'll be 2300 amps. And if the resistance is 0.01 of an ohm, then the current will rise to 23,000 amps. The resistance below 0.01 of an ohm is normal in industrial installation. Short circuits. It follows that the equipment chosen for a particular duty must be able to withstand the fault level it may be subject to or have to interrupt. The rated circuit breaking current relates to the device such as fuses, circuit breakers, which are intended to break the fault current. In the past, such devices were related in terms of their power interrupting capability, which was arrived at as the product of the rated fault currents the device was capable of breaking. The rated voltage was expressed in MVA. Nowadays, it's recognized that the current which a circuit breaker can interrupt is not related to the voltage, and then the two values of the breaking current and the system voltage are given separately. However, this issue is worth mentioning since the old practice is by no means dead, particularly in American markets, and system planning engineers find it convenient to calculate fault levels in MVA. The rated short circuit breaking current is the maximum symmetrical RMS current that the circuit breaker can interrupt at its rated voltage. It usually is quoted in kA. The rated making current and short time current are related. The peak current can arise when a short circuit occurs and has to be withstood by the switching device. If the device is not called upon by the protective system to clear the fault, it will also have to withstand the thermal effects of carrying the short circuit current for a short time until some other device interrupts it. The ratio of reactance to resistance of the system in which the short circuit occurs, together with the relationship between the time when the fault is made and voltage zero, control the magnitude of the making current peak. International standards make assumptions concerning the ratio of inductance to resistance of the system under short circuit conditions, which will cover the vast majority of electrical networks. The short time rating is practically always the same as the rated breaking current for the circuit breaking device, and an identical scale of value is used for the non-breaking fault equipment. The standard values for the duration of the short time current are 1 and 3 seconds. The value is chosen dependent on the characteristics of the protection system being used. In assessing the need for one value, the other is usually to assume that the first line of defense in the protection system might fail, and the time for which the fault current persists then depends on the backup protection. As a general rule, the more extensive the network, the more likely it is to have a higher figure. Also, in networks where the installation began many years ago with the earlier forms of relays or other protective devices, the need for wider tolerances at different levels of discrimination again leads to choosing the higher value. Switchgear definitions. A disconnector is a device used to create a safe gap in an electrical system, and its important characteristics are to withstand the system voltage and any overvoltage which may be generated in the system. It is intended to be operated off-load, i.e. other switching devices must be used to break any current flowing in the circuit before the disconnector is operated, unless the system is such that there is a negligible voltage across the contact gap. A switch is required to be able to open an electrical circuit carrying any current up to its rated continuous current or up to some defined level of overload. Because it's used to perform switching operations on loaded circuits, there is a possibility that it might be closed onto a faulty circuit, i.e. one which has an earth or a phase-to-phase fault or similar. If the switch can also perform the function of a disconnector, i.e. it has the required insulation levels to earth and across the gap, it's called a switch disconnector. If fuses are added to the switch so that it can then interrupt short circuit currents, it becomes a switch and fuse combination, and two forms of this device are recognized. A fuse switch, a switching device which is the fuse link or the fuse carrier with the fuse link forms the contacts of the combination. A switch fuse is a switching device in which the fuses are connected in series with the switch in a combined assembly. In commonly used versions of these devices at medium voltages, the fuse is only intended to deal with the short circuits, and the switch has the breaking capacity in respect of the overload that overlaps the fuse performance. A circuit breaker has the most onerous duty to perform any of the switching devices. It has to be capable of interrupting any current that may pass through it up to its rated short circuit breaking current. It must also be able to close on the peak fault current and carry that fault current for a predetermined period of time. Introduction to the protection system and the relay. Faults on power systems manifest themselves by high currents. The consequences of not removing a fault from a system would be damage to the faulted part of the system, damage to the healthy part of the system, loss of synchronism, and the consequently splitting of a system. The function of a protection on power system is to detect and remove the faulted parts as fast and as selectively as possible. A well-designed protective system should be reliable, which means it's capable of detecting all types of faults, selective, in isolating only the faulted parts of the system, fast, economical, and simple, the minimum amount of equipment and circuitry. Types of protection relays. Auxiliary relays are used to assist other relays or devices to perform their function. Example of this would be timing relays or interposing relays. Protective relays are used to detect faults and initiate switching. Examples of these would be overcurrent relays or impedance relays. Regulating relays are used to detect a departure from a predetermined quantity and to initiate corrective action to get the quantity back within its limits. An example of this would be a frequency relay or a voltage relay used for voltage regulation. Verification relays are used to verify the conditions of a power system. Example of this would be alarm relays. Another classification for relays is according to their speed. We have high speed relays where the operation time are 3 cycles or less, and then we have low speed relays for an operation time of over 3 cycles. Advantage of using high speed relays is minimizing the amount of damage to the system during a fault. The disadvantage to it is they're of a higher cost and there's an increased probability of incorrect operation during transient conditions. Each relay used for a power system protection performs a certain function and responds to a change in a certain quantity. The quantities to which the relays respond are increased current in one or more phases, the direction of the current flow, reduced voltage, direction of the power flow, frequency, the ratio of voltage and current. According to their functions, relays are classified as current relays, directional and non-directional, voltage relays, impedance relays, also known as distance relays, power relays, differential relays, and frequency relays. The power system is divided into zones. Each section is either a transmission line or a piece of a major equipment, transformer, or a generator. The zones overlap to avoid leaving any area without protection. The overlap zones is usually achieved by overlapping the connection to the current transformers. Zones of protection A. This covers the cable connection from HV switchgear to the HV terminals in the transformer. Fault current levels in this zone depend on the short circuit power available at the HV substation, which is usually defined by the supply authority. The cable impedance can be neglected, and therefore the fault level can be considered to be constant throughout the HV distribution system. If the 20 kV system is solidly earthed, the phase fault earth level will be the same order as the 3-phase fault level. Earth faults can be isolated within the required time by the HV overcurrent protection. In networks where the earth fault current is limited by the use of a neutral earthing impedance, it is possible that the overcurrent protection will not meet the speed and sensitivity requirements for the isolation of the phase earth faults. In this case, a dedicated earth fault relay is connected to measure the residual current will be required. Zones of protection B. This covers the transformer itself. The HV overcurrent protection must detect and isolate faults within this zone. A buccal or pressure relay, where fitted, will operate for all faults within this zone and cover some fault conditions which the overcurrent protection cannot detect. Current on the HV side of transformer fault current levels, or an internal fault, overcurrent protection has limited sensitivity for this type of fault, as there is no significant increase in the current drawn by the HV windings. An overcurrent relay with the setting of 120% of the rated current will detect a minimum of 2% of the shortened turns. A buccal or pressure relay should be used for greater sensitivity. Earth faults on the HV delta winding. A 1 MVA transformer typically has an impedance for through current conditions of 5% based on transformer rating. For a fault at the centre of one leg of the delta winding, the impedance is typically 25 to 50%. This is relatively high impedance results for a low current for a fault occurring at the midpoint of a winding. Typically of the same order the transformer rated current, since only half of the normal phase voltage is applied. In addition, the fault current flows into the fault from both ends of the winding and is split between the two phases of the system. The actual phase currents therefore can be less than normal load current, and this condition cannot be detected by the HV overcurrent relay. The fault could be detected by either a buccal relay or an earth fault relay on the HV side if these devices are fitted. Earth faults on the LV star winding. As the majority of the installations in this country have a solidly earthed connection on the distribution transformer LV windings, this is the only situation considered here. The level of the earth fault current depends on the driving voltage, which is directly proportional to the distance of the fault from the neutral point and the impedance of the transformer winding. The impedance of the windings varies in a complex manner and rapidly falls to a very low value near the neutral point. This results in a relatively high current flowing in earth faults near to the neutral point, even though the driving voltage is low. Since the turns of the LV winding are shorted out by earth fault, the effect turns ratio of the transformer is reduced for faults near to the neutral point. Thus, even though a high current may flow on the LV side, this is not reflected on the HV side. Fault current on an LV phase earth fault. Even if an earth fault protection is fitted on the HV side of the distribution transformer, it would not see any earth faults on the LV part due to the presence of the delta winding. Therefore, it will not respond to this fault condition. A HV overcurrent relay set to 120% of the normal rated current will only provide protection for earth faults on 90% of the LV windings. In addition, as a lower current is reflected on the HV side, clearance times for the overcurrent protection will be slow and may be unacceptable. A restricted earth fault relay applied to the LV side can cover up to 95% of the windings and will operate in about 25 milliseconds for any faults occurring within the zone. Bugles or pressure protection will cover the remaining 5%. Overcurrent relays. Principles of overcurrent relays. Overcurrent relays are used for the protection of lines, transformers, generators and motors, and there are two types: instantaneous and time overcurrent. Instantaneous relays, high set, operate without the intentional time delay. They're used for faults to close the source when the fault current is very high. The operating times are approximately 30 to 100 milliseconds. Time overcurrent relays, are low set, operate with a time delay. The time delay is adjustable for a given setting, and the actual time depends on the current flowing through the relay. In general, high current will cause faster operation of the relay. The minimum current at which the relay operates, or the pickup current, is also adjustable. Principles of overcurrent relays. Low set element. The pickup current is determined according to the maximum load current. For example, current transformer ratios of 400 to 1, maximum expected load at 300 amps, overload coefficient is 1.2, which is assumed, and the start current setting would be IS is equal to 300 over 400 multiplied by 1.2, which is 0.9 times IN. Time multiplier setting. The time multiplier setting for inverse time overcurrent is a scale factor for the selective characteristics. The characteristics of two adjacent relays should have a time interval of about 100 milliseconds. Types of overcurrent and calculations. Overload. Operation of equipment in excess of normal full load rating or of a conductor in excess of the rated current carrying capacity that, when it persists in such a sufficient length of time, will cause damage or dangerous overheating. A fault such as a short circuit or an earth fault is not an overload. Overcurrent. Any current in excess of the rated current of equipment or the current carrying capacity of a conductor. It may result from an overload, a short circuit or a ground fault. Faults and type of faults. There are bolted faults and arc faults. Bolted faults are where you've got a physical connection between the short circuit, and an arcing fault is where the current jumps through air from conductor to conductor. There are various types of bolted fault. Just three phase, typically considered the worst case scenario for highest magnitude. Solidly earthed phase to phase, 80% of three phase bolted faults occur in this manner. Arcing faults, many variable affect current and whether sustainable. System voltage gap spacing, available three-phase short circuit current, amount of copper vaporized, the degree of containment, and the configuration of equipment. An example of which: they can widely vary, a possibility of up to 89% of three-phase bolted faults occur in this fashion. A line to ground earth fault. These can vary greatly. Rule of thumb for arcing faults will typically not sustain less than 38% of a three-phase bolted fault. Differential relays. Basic current differential relaying. Current differential relaying is applied to protect many elements of a power system. The simplest example of current differential relaying scheme is shown in the figure below. The protection element might be the length of a circuit conductor, a generator winding, a bus section or transformer. From figure 1 it can be seen that the current differential relaying is basic application of Kirchhoff's law. The relay operates on the sum of the currents flowing in the CT secondary. For through two current conditions such as load and external fault, the currents in the two CTs will be equal in magnitude and opposite in phase, assuming that the CTs have the same ratio and are properly connected, and there will be no current flowing in the operated relay. Should the short circuit occur within the protection section between the two CTs, current will flow through the operated circuit, causing the relay to issue a trip output. To improve the selectivity and security of the current differential scheme, it is often designed as a percentage restraint differential relay. In a percentage restraint current differential relay, the operated current is the vector sum of the CT currents. This operated current must be greater than some percentage, K1, of the restraint quantity, which is derived from the sum of the magnitude of the individual CT currents. A typical restraint current could be I restraint is equal to K times I1 plus I2. The operating characteristics of the percentage restraint current differential relay with the slope K1 is shown in figure 2. The traditional percentage restraint characteristic shown in figure 2 is commonly used in the current differential relays. It may also be modified for the use of dual slope restraint as shown in figure 3. The dual slope percentage restraint characteristic improves the security of the current differential relay for faults external to the protected zone. This is of the particular advantage because the current transformers may not accurately reproduce the primary fault currents under transient fault conditions. The dual slope restraint characteristic is a form of adaptive restraint, which is a magnitude of the restraint quantity is increased for a higher current condition where the CT accuracy is worse and CT saturation becomes more probable. In order to avoid tripping during energization, transformer differential relays have an even further restraint element. This element restraint the tripping of the relay on the detection of even harmonic currents, normally in the second harmonic. Magnetizing currents or inrush currents in a transformer contain a high level of second harmonic current. The presence of these harmonics allows the relay to distinguish between a fault and the protected zone, and the transformer has been energized. Fault currents in general contain little or no harmonic currents. Voltage control, otherwise known as tap change. What is a transformer tap changer and what does it do? A tap changer is a device fitted to a power transformer for the regulation of the output voltage to a required level. This is normally achieved by changing the ratio of the transformers on the system by altering the number of turns in one winding of the appropriate transformer. International standards require that supply voltage to be kept within certain limits. Tap changers offer variable controls to keep the voltage supply within these limits. About 96% of all power transformers today above 5 MVA incorporate on-load tap changers as a means of voltage regulation. Tap changers can be on-load or off-load. On-load tap changers generally consist of a diverter switch and a selector switch operating as a unit to effect current transfer from one tap to the next. Here's an example of a voltage tap diagram. Tap changers possess two fundamental features. The first feature is some form of impedance is present to prevent short-circuiting of a tap section. And the second is a duplicate circuit which is provided so that a load current can be carried by one circuit whilst switching is carried out on the other. The impedance mentioned can either be resistive or reactive. High-speed resistor switching is now the most popular used method. At lower voltages, the tap changer may be located at either the low voltage or the high voltage winding side. Tap changers can be connected to the primary or secondary side windings of the transformer dependent on the following: the current rating of the transformer, the insulation levels present, the type and winding of the transformer, whether it be star, star delta or an auto transformer, position of the tap changer in the winding, losses associated with the tap change configuration, step voltage and circulating currents, cost and the physical size. Voltage regulation relays. The purpose of the regulator is to maintain stable secondary voltage to the power transformer. The basis for this operation is the reference voltage, which is set by the user. By adding or decreasing compensation factors, the regulator calculates a control voltage from the reference voltage. On the other hand, a measured voltage be outside of these band limits, an adjustable delay T1 starts. This T1 remains active as long as the measured voltage is outside the hysteresis limits of the bandwidth. The standard setting of the hysteresis limits is 90%. Should the measured voltage be outside the hysteresis, when the delay counter reaches its setting value, the raise or lower output relay is activated and the motor drive of the tap changer is operated. If, on the other hand, the measured voltage falls within the hysteresis limits, the delay counter is reset. Should one tap change operation not be enough to regulate the transformer voltage within its hysteresis limits, a second adjustable delay, T2, usually with a shorter time setting than T1, starts. The delays T1 and T2 can be selective either with definite or inverse time characteristics. Inverse time characteristics means that the delay is inversely proportional to the regulator error, i.e. the delay is inversely proportional to the difference between the control voltage and the measured voltage. The setting voltage can be selected between 90 and 139 volts in 0.1 volt steps. The relay compares the system input voltage with this setting voltage and provides raise or lower signals to the tap changer to control the system voltage within its deadband limits. The deadband limits are defined as DVS percentage or the VS percentage setting and are dependent on the tap step increment of the regulating transformer. Typically, the DVS percentage is equal to plus or minus 1% for an average tap step increment of 1.4% of the transformer. The deadband can be set between 0.5 to 5% of the VS. The time delay to initiate the tap change sequence is set by the initial time delay setting between 0 and 120 seconds. A software function link, control link 2, determines the setting either definite or inverse time characteristic. Where multiple tap change sequence is required to bring the voltage back within deadband limits when the time delay between the successive tapping outputs can be set between 0 and 120 seconds. This is normally set to be slightly longer than the operation time of the tap change mechanism. The intertap delay starts after the initial time delay has elapsed. When the initial time has elapsed, the output continues to give pulse closure for the tap pulse duration at intervals set by the intertap delay. Setting the intertap delay to 0 seconds results in continuous output indicated by the illuminated control LED. Voltage regulation relay. Under voltage detection. An independent control to detect undervoltage conditions between 80 and 100 volts. This function may be used to block operations that would lower the line voltage further, thus defining the minimum working limit of the transformer. Overvoltage detection is the independent control provided to detect overvoltage conditions set between 110 and 160 volts. This function may be used to block operations that would raise the voltage further, to prevent the excessive voltage on bus bars to the local transformer. Under voltage blocking. The under voltage blocking setting can be set between 60 and 130 volts. Where the system voltage falls below a set value, the under voltage detector operates and instantaneously resets the initial time delay, thus inhibiting the relay and the raise and lower tap change operation. Circulating current detector. The excessive circulating current detector settings can be set between 5 and 50% IN. In the event of excessive circulating current over a time period set between 0 and 180 seconds, the detector can be used to internally block the relay from both raise and lower operations and set an alarm. Circulating current protection is normally applied when it is intended to operate transformers fitted with the OLTC or on-load tap change protection in parallel. Overcurrent detector. The overcurrent detector setting can be set between 50 and 200% of IN. An alarm can be indicated if the load exceeds this setting. Number of tap change operations. The total number of tap change operations can be set between 1 and 10,000. An alarm is initiated if the number of operations exceed the set value. Tap change operations. The total number of tap changes allowed in a time period can be set between 1 and 100 for a time period and can be set between 0 and 24 hours. An alarm is initiated if the number of tap operations exceed the preset value for a preset period of time. Tap fail time delay. Alarm initiation time delay can be set between 0 and 15 minutes. An alarm is initiated if the voltage has changed due to the tap operation in response to a valid raise lower command issued by the relay, but is unable to come with a prescribed deadband limits within the period of the preset time delay. Total taps available. The total number of taps available can be set between 1 and 40. Two threshold settings, maximum tap position and minimum tap position, can also be set between 1 and 40. An alarm will be initiated if the tap position indication is outside of these set thresholds. Warning: under no circumstances should the secondaries of current transformers under load be open circuited. The open circuit voltage of a CT can reach several thousand times its voltage and is lethal. Instrument and protection CTs. Current transformers are used to supply information to the protective relays and our current, power and energy metering instruments. For this purpose, they must supply a secondary current proportional to the primary current flowing through them, and must be adapted to the network characteristics for voltage, frequency and current. They are defined by their ratio, power and accuracy class. Their class is an accuracy of a function of the CT load and of its overcurrent. It is chosen according to the application. A protection class CT must saturate sufficiently high to allow a relatively accurate measurement of the fault current by the protection, whose operating threshold can be very high. Current transformers are thus expected to have an accuracy limit factor that is usually fairly high. Note that the associated relay must be able to withstand high currents. Open the secondaries of a transformer for testing should only be done where proper drop link terminals are fitted and shorting links provided. An instrument CT requires good accuracy around the nominal current value. The metering instruments do not need to withstand currents as high as the protection relays. This is why the instrument CT, unlike the protection CT, have the lowest possible safety factor in order to protect these instruments through earlier saturation. Some CTs have secondary windings dedicated to protection and metering. These instrument and protection CTs are governed by the standard IEC 60044-1 for the general application. The matching of CTs with protection relays calls for a thorough knowledge of CTs. Instrument and protection CTs. An example of a protection current transformer. A rated primary current of 200 amps, a secondary rated current of 5 amps, 15 VA, 5P10. The accuracy limit factor is equal to 10. The accuracy class is equal to 5P. The accuracy power is 15 VA. Its accuracy load PN is equal to 15 VA. Its accuracy limit factor is ALF is equal to 10, for I is equal to ALF, and its accuracy is 5%. To simplify, for the protection CT given in this example, the error ratio is less than 5% at 10 times IN. The reload consumes 15 VA at IN. Here's some tables of the accuracy classes and the functions. So an accuracy class of 0.1 would be used for metering, whereas if you move down to 5P, it would be used for protection. Voltage transformers and VTs. Voltage transformers are categorized similar to CTs in terms of accuracy and burden. However, unlike current transformers, they should never be short-circuited. Voltage transformers are used for voltage regulation relays, metering and protection. An example of protection where VTs would be used would be directional overcurrent and earth fault protection using an open delta configuration. Power transformers. There are two basic types of distribution transformer in common use today. In one which the core and windings are enclosed in a liquid-filled tank which provides cooling and insulation, and the other where the cores and windings are cooled directly by air. Liquid-filled transformers can again be subdivided into units rising to flammable substances such as mineral oil, and those using various types of fire-resistant liquid such as silicone liquid or synthetic hydrocarbons. Dry-type transformers are also available in two distinct types, with the insulated turns of the windings directly in contact with the cooling air, and those with the complete windings encapsulated within a moisture-resistant cladding of epoxy resin. The ratings of individual transformers within installations are determined by load requirements, the physical space available, the distribution system voltage regulation, and the high voltage switchgear fault rating. The heart of the conventional three-phase distribution system is laminated. The electrical sheet steel core in 3 limbs. Each limb carries 2 concentrically wound coils. The secondary, the low voltage, is inside. The nearest the core and primary high voltage is on the outside. The whole is contained within an enclosure of steel. In the case of a liquid-filled transformer, the enclosure consists of a leak-proof tank, while the dry-type transformer merely requires ventilating casing of the enclosed live parts. Some designs of dry transformers are totally enclosed in a non-ventilated sheet steel housing and have an IP rating of up to 55 to BS 5490. These transformers are used in installations where environmental contamination would preclude the use of conventional dry-type designs. Their superior resistance to fire is required. Transformer tappings are usually included on the HV windings of distribution transformers to alter the turns ratio between high and low voltage windings. They thereby compensate for variations in the primary supply voltage in order to maintain the consumer voltage within its statutory limits. On distribution transformer taps are selected by means of an off-circuit device. The transformer must be disconnected from the supply before the taps can be changed. A few years ago, the standard distribution transformer had no tappings. It is argued with a fully regulated 10 or 11 kV supply system, as existing in most Western countries, tapping on distribution transformers are entirely unnecessary. The standard off-circuit tapping range is 10%, with 2 taps of 2.5% above normal and 2 taps of 2.5% below normal. In especially difficult areas, most transformer manufacturers will be quite happy to supply this range all in negative taps. It is generally agreed that there should be some movement towards voltage standardization within the EU. Inevitably, the recommendations for voltage standardization are almost as numerous as the countries involved, and the rationalization may well involve the extended tapping range. Off-circuit taps on distribution transformers are normally selected by a switch on a liquid immersed transformer and on links on a dry-type transformer. 3 and 5 position tap switches are the most common in Europe. In certain difficult areas of the world, it is not unusual to see off-circuit tapping ranges of 15 or even 25% specified. Transformer connections. Most 10 and 20 kV distribution systems are supplied through system network transformers where the LV winding is in star connected. The system is therefore earthed via the neutral of the network or the system transformer. For satisfactory elimination of triple frequency harmonics, it follows that 10-20 kV windings of the distribution transformers should be delta connected. It is necessary on LV domestic distribution systems that phased to neutral voltages are available and that the neutral operates at or near to earth potential. The most common winding connections are therefore either DY11, DY1, DY5 or DY7 with DY11, or its equivalent being widely used throughout the world. These connections are defined in BS 171. Transformer connections. The vector relating to the HV windings is taken as the vector of the origin, and the secondary phase relationship is related to the clock face. For example, DY1, where the secondary star lags the primary by 30 degrees, corresponds to 1 o'clock. The choice of phase relationship between the primary and the secondary winding is unimportant if one transformer is to be given a site network. However, if it is more than one transformer that's involved, then they must all have the same phase relationship. Otherwise, it's impossible to parallel them or to switch them over supply to the network from one transformer to the other. Transformer parallel operation. The satisfactory operation of transformers in parallel means that each transformer will carry its share of the load according to its rating. Transformers in parallel must have the same secondary voltage for a common primary input. The choice of a phase relationship between the primary and secondary windings is unimportant if only one transformer is used for a given site network. For this condition to be met, the voltage ratio, phase displacement and impedance must all be the same. The importance of this phase displacement is obvious. A pair of three-phase transformers or similar characteristics have the same connection symbols can be operated physically and alphabetically. For example, DY1 and YD1 can safely be connected together. The impedance which governs the regulation decides the proportion of the total load which is taken by each transformer. The resistances of each unit must be similar. When connecting the units in parallel or paralleling supplies from two separate transformers, the phase rotation must be the same. The other point to remember when paralleling transformers is the testing impedance of the two transformers can vary by 10% of the guaranteed value. Two transformers to the same guaranteed value impedance can have test values which can vary as much as 20%. The length and type of cable connection must be considered if additional transformers capacity is added to the existing system and sited away from the original unit. Transformers that have tapping ranges larger than 10% need to have the impedance variation through the tapping range considered. Very large variations between the manufacturers can occur owing to different winding arrangements. And that concludes the presentation in relation to operation of electrical installations. If you have any queries, get in contact with us in the contact details provided. I hope our presentation has been entertaining. Thank you very much.